Son bir kez daha bugün için hepinize hoş geldiniz diyorum. Bu son bölümü bize Mohsen anlatacak. QuTiP'e giriş dersi verecek. Bu bölüm İngilizce olacak. So since this session will be in English, I would like to welcome everyone and also Mohsen in English again. For this last part, Mohsen Izadyari will give us the QuTiP'e introduction lecture. He is a PhD student in Koç University right now. He's studying with Özgür Müstecaplıoğlu. So thank you, Mohsen, for accepting our invitation. And you can start.
Thank you, Deniz. At first, I'm going to thank Onur and Gökhan Hoca because of their interesting talk. I will start with the QuTiP'e introduction for the quantum information theory today. At first, I'm going to just have some introduction for what is the QuTiPe and how we can download it and install it in our computer and use it. In fact, at first, the QuTiPe is one of the libraries in the Python, and you can just a minute. You can go to this website and download the QuTiPe, and there is the installation, how you can install the QuTiPe in your Python. I recommend you using the Anaconda to install it. And also there is some documentation, and here you can find some in fact PDF documentation or online documentation for how you can use it in your Python environment, and also you can learn about a lot of examples for the quantum mechanics. In fact, the QuTiPe is a quantum toolbox, especially very good for the open systems, and you can use it for the quantum information and all generally for the quantum physics calculations. Now I'm going to start with some simple examples and how you can use it. You know that there is a key difference between the classical and quantum mechanics, and it lies to the operators and how you can introduce your in fact states. There is a difference between the quantum states and classical states, and the QuTiPe provide you some things that you can use the state as a quantum object. As you can see that there's a quantum object here. If you install the QuTiPe and in the Python environment, you can use that Spider or other notebooks in the Python. When you write the Q object, the output will be something like that. That this is a quantum object. Dimensions is 1, 1, and this is the shape of the your state. And you can introduce different objects based on what you need. And for example, you can introduce an array here, and it will be the quantum object when you use the QuTiPe. And there are a lot of functions that in the quantum mechanics you will need, and in the calculation, especially in the quantum optics or quantum open system, that you can find it here. And for the quantum information, there is some Pauli matrices are very important that you can just by using this command you can use them in the calculations. And no, I'm going to I want to in fact use some simple examples to understanding the environment, and then to have a motivation to use that this QT for your simulations. One of the important things in the quantum mechanics that we need is the expectation values. And as an example, you can consider here we have we can introduce the Q bit, and in the Q bit we have two states, 0 and 1. By matrix we can introduce like that. And I'm going to find the expectation value of the SZ, and this is the mathematics of the what we are going to find. And but in the QuTiPe, how we can find it? I can in fact introduce the states for the 0 by I call it up as a basis of 2 and 0. Basis gives us the quantum state, and 2 and 0, 2 means the 2 dimensions, and 0, this is the 0. In fact, in this states we have 1, and the other one is 0. So you know that in the Python the values are start from the 0. So if we have if we want to mention this part, we should write 0, and for this one we should write 1. No, finding the expectation value, it's very easy. You just need to write the expect, and writing your operator, and as a here I just want to use SZ, and it will be sigma Z, and after that which state we want to find the expectation value, because I introduce up as this state, so I just write this and find that. So you can see that it's equal to 1. And for the second state, it is the same thing, and it will be the -1. So you need just write expect, write the operator, and state what you want to, in fact, find the expectation values. In the quantum, in fact, the information and the quantum computation, we need tensor products. And the first step with ONU, you find that it's in fact importance. If I have any unstable connection, please let me know, because okay. For the tensor products, we just need to write the tensor and write the two bases, in fact, two states that we want to find. We want to find the tensor product between them. Here, this is one of the examples that, for example, if I want to find the tensor product of the 0 and 0, I need to write the tensor and write the two bases that I want to calculate. This is the same for the operators here. This is what I'm going to calculate, and this is our calculations in the QT. So after introducing the tensor product in the QT, what we need is the partial trace. Here, this is the partial trace. This is again a very simple that the partial trace for your system. And I'm going to again by taking an example show you how you can use it. For example, if we have 2 qubit spin singlet state like this one, so you can find that. And I'm going to at first introduce the density matrix for this state, and this is the density matrix. and then I'm going to find the partial trace for that. If I eliminate the B part, the system B, and part trace over the B, sorry, I should write at first. I will write the state, this psi I introduced before, and then when I the output will be something like that. This is our state, and if I want to in fact trace over the second system B, so I should write here the 0, because we have two systems, 0 and 1. So I just need to write the state or the density matrix. It's up to you. You can do it both of them. So I will write the state dot p trace and what system I want to eliminate. I want to eliminate the second one, and so I should write the 0 here. And this is the same for the second system. So if I want to have a partial trace over B, so I would write it here 0. Partial trace over A, I should write here 1. Okay, now I'm going to find the more information tools in the QuTiPe, and in the quantum information there are a lot of functions that we can use in the QuTiPe, and the comments are very simple. You can see here there is a one Newman entropy, and the comment will be just one Newman entropy, one Newman, and you should you just need the density matrix. So by having the density matrix, you can find the one Newman entropy, also the linear entropy for the finding the if your system is in fact pure or it's not, and if your system is mixed state or pure state, and also mutual entropy. You can find that. I mean, this is here. If you want to find A to B, so you should write here 0 and 1. And for the B to A, you should write here 1 and 0. And you need you just did the density matrix of that system. And also for concurrence and negativity, it's the same, and it is very, in fact, simple comments. No, I'm going to take an example for these comments, and I want to show you this this calculation in the Python environment. So let me. Okay, I hope you can see them. Okay, here at first in the Python environment, in the here I'm using in fact a spider environment for my Python. So at first I introduced the basis S1 and S2. This is the 0 and 1 in our quantum information calculations, and this is the SP. This is the superposition between the S1 and S2. And no, because I want to, in fact, introduce these states, so I need to use the tensor product. So you can see here, psi1, it's the tensor product of S1 and S1 again. This is our this state. And for 1 and 1, it's again the same thing. Sorry. We have the psi2, this one. And also for the third one, row 3, we have here, this I'm going to write this one in the Python. You can see that this is our row 3 tensor product of these elements. And here you can see we have the bra and kit. This kit and bra, I can write the bra as a kit, dagger of the kit. So if I here introduce S1 as a basis, this is a kit, and when I want to use it as a bra, so I can easily write as a dagger of that. So just to use dot dag, so you can find dagger of the every state, all the states, or even operators. Okay, this is our states, and easily I can just write these comments for finding the von Neumann entropy, concurrence, and the entropy, linear entropy, and I am going to run it here. So, okay, no, you can see here, this is the V1. I can write in this here to as a print V1 and V2. I didn't do it, but you can find that when I V1 call V2, it's again about 3. For the concurrence, we know the second example was the entangled states. So you can see here. I wrote them here as you can see, this is the psi1, the von Neumann entropy, linear entropy, and concurrence is 0, and we knew that this is our this state, and this is the pure state. And for the second one, just our system is entangled, so this is again the pure entangled state because this linear is again 0. But for the third one, the rotary or density matrix, it's not entangled, but it's not pure because the linear entropy is 0.5. Okay, so let me again go to in fact just sorry, I'm trying to okay no, I'm going to talk about the quantum Discord. Here I'm going to do some calculations about what Gökhan showed you in the last part. And this is the definition of the quantum Discord, as you know that. And here there is calculations. We are going to find the Discord for the row AB. This is our state, and this is depend on the P, and we are going to find the effect of P on our system and find the Discord, entanglement, linear entropy, and also the von Neumann entropy for that. There are some calculations for the finding the Discord that Gökhan told you, and I just want to have a quick review for that. There is a P1, P2, and this is the row B that we have two in fact bases for the measurements, 0, 0, and 1, 1. And finally, after as an analytical, we can find this one. So in the how we can use it in the in QuTiPe. No, this is my program for the QuTiPe. Again, at first I should import the QuTiPe to our system, and there are some other libraries for calculations. Because I want to use different P's here, so I'm going to introduce P different values of P. So I introduce in fact, space for the D as a discord concurrence, L for the linear entropy, and von Neumann entropy. Again, we have we should introduce the U1 and UT as a basis of, in fact, the 0 and 1 states of qubit. And this is UP. S is, in fact, I write it the values between 0 to 1. I'm going to introduce the values for the P. So, and it will divide it to 100 values. And then I use the 4 for that values of the P. This is our row AB. I call it here row 0. Okay, and this is the, I introduce some different, in fact, values to, in fact, simplify the calculations and summary the calculations here. For the P1, as you can see here, this is here, this is a P1, so I need to trace over this value. So I write it here. This is, in fact, sorry, the tensor product of these values. And this is the in fact, definition of the row B1 and row B2 that you can see here. This is these two, in fact, states. And finally, also you can find the eigenvalues of the system by a very simple, in fact, command that in the Python you can use it. It's not dependent on the QuTiPe. And also, no, I'm going to write some comment for the coming from the QuTiPe. This is von Neumann entropy of the row 0. And for the row A and row B, what's the row A and row B? Are the partial trace of the in fact, initial state over the systems A and B. And finally, I introduced the discord for that. This is the, in fact, von Neumann entropy of the row A minus the von Neumann entropy of row AB, in fact, and this is the definition of the that you can see here. This is this parameters, and finally. For the discord, you can introduce this one. Okay. Now I'm going to plot them, and I write also the concurrence and entropy linear for our row 1, in fact row AB. So when I run it, I will find these figures, and I will show you here. Okay, you can see that this is our row AB, and by calculations over the discord, you can find that the discord are increasing until the this value about 0.4. I don't know exactly. And again, for the P0, it's 0, and for the P1, it's again 0. And the entanglement, the concurrence is the 0, so this set is completely, it's not entangled. And von Neumann entropy is increasing until for the P equal to 0.5, like a linear entropy. So when we have in fact, the maximum mixed state, the von Neumann entropy is the maximum. But for the here you can see for the, in fact, discord, it's not maximum. So this is what I wanted to introduce as an introduction of the, in fact, QTiPe. I hope it's some motivation for you to have to be familiar with this library in the Python, and it makes the calculations easy, really. And I recommend you to be familiar with this QTiPe. And that's it.
Thank you, Mohsen.
I didn't know anything about time. How many times?
You are really on time.
Okay, thank you. It's good.
Soru sormak isteyen varsa Mohsen için şimdi alabiliriz. Ben İngilizceye çevirebilirim. I think right now there is no question.
Okay.
We have a question.